Okay, here we start section 4.2, and the first thing we start with is just the sigma notation. Okay, so the idea is, suppose you want to add up a bunch of things, and really I'm going to start a little bit different differently than they do, and in that, suppose I have a function, and doesn't really matter what it is, but just for concreteness, suppose I have that function. I'm going to name it a of x, and suppose it's x squared, and for whatever reason, what I would like to do is I would like to add up, say, a of 1 plus a of 2 plus a of 3 plus a of 4, and we'll stop at a of 5. Okay, I want to point out a couple things about this thing here. Well, so a of x is x squared, but suppose, I really don't want the domain to be all real numbers. Okay, so suppose the domain is actually just the numbers, say 1, 2, 3, 4, so the positive integers. Now, I could start with the non-negative integers, 0, 1, 2, 3, 4, and so forth. I could even go to all integers. Now, trying to write that down, so I could look at, say 0, -1, +1, and -2 and +2, and so forth. Okay, so suppose my domain has something to do with the integers, though, not all real numbers. Then typically in math, although you shouldn't, if you just see something like this, you shouldn't assume it's only integers or something along those lines. But often we'll use, instead of an x, we'll use an n. So what we really may be talking about is a function a of n equal n squared, where n could equal 1, 2, 3, 4, and on to infinity. So that's one thing, is just that you can't just always assume that if you see an n as the independent variable that you have only the integers, or say the positive integers or something like that, but it's a clue that that may be what's going on. Then the other thing is, well, we have the a of notation, right? So a of something, so in parentheses. Well, you could have other notations, and actually another notation could be a subscript. Okay, so I use this underline right now for a subscript to show it as a subscript, because in LaTeX, a particular typesetting thing that I use, that's how you would make a subscript. But what we're saying is a sub n, like that. And partly I use that line there kind of like the parentheses, but now I don't even have to use the parentheses. So the subscript notation here is really just a different notation for functions. But typically you'll only see it when the function is somehow just dealing with integers. and often say a sequence of integers, 1, 2, 3, 4, 5, and up, or starting at 0, or starting at -2 and going up. That's when you'll see that notation. But that's all that notation is really a different way to say a function. So you could say, a sub n is n squared. And so that notation, if I didn't see the 1, 2, 3, 4, and so forth, n equals 1, 2, 3, 4, I would probably guess, though, because it's in a subscript notation and it's using an n, and we'll see other letters like K, I, J. So typically when we're using the integers, we might start at I and use usually a script L that doesn't look like a 1, L, M, or N. So those, often we'll use those as our independent variable when we're talking about integers. And so then another word for that value n could be the index. Okay, n is the index. Okay, so when I see this notation, there's a little better n, I guess, I can call n the index. Okay, but really all it is it's a slightly different notation than what you are used to, like that. Now you may not, just like we sometimes would say f of x. Well, so you may not know what a sub n is, but it's just some function evaluated at n, okay, or evaluated at x or whatever. So, okay, so that is this notation, n is an index, and so we could now talk about adding up a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And in our particular case, where we said a sub n is n squared, that would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, so it's a very simple task. I mean, we're just adding. We have to evaluate our function, but we're just adding things up. Now, as you can imagine, this could get really nasty as we get more and more terms to add up. So suppose I wanted to add a sub 1, a sub 2, a sub 3, all the way up to a sub 152. Yeah, it gets a lot to write and so forth. So we have a compact notation, and we call that the sigma notation. Okay, so there's our sigma notation, and we let a reader or someone know we're doing a sum by using this uppercase sigma, like that. And then, in the most general way, we would say, oh, okay, let's add up a bunch of evaluations of our function a at different values. And so here's where we maybe switch to an I or something like that, is we would say a sub I, which you can think of as a of I, right? So it's whatever our function is. And but just saying I want to add up a bunch of these doesn't tell me which ones to add up. So somewhere I need to let you know that. And so what we do is we say, well, I starts at 1 and in this case ends at 5. And so that notation exactly means to take A1 plus A2 plus A3 plus A4 plus A5. Which, if we know what A is, in our case, A of A sub n was n squared, that would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. But we could just do it as the, defining what A was in the summation as we do it. So we could say, well, this is the sum, I equals 1 to 5, and tell you what A sub I is. Well, that was I squared, right? If, we come back up here, this is what A sub n is the n squared, so A sub I would be I squared. And so we could write it like that. Okay, so that is the idea of sigma notation. You can use whatever letters you want, but that's, again, you tend to see I, J, K, L, M, and N. Okay, so another example with sigma notation is let's see, we'll add a page here. I thought I'd add a page. There we go. Add a page, and so I could have something more general, like, I want to do the sum I equals 1 to n of I. Okay, so I just want to add those up. Well, that means I want to do 1 plus 2 plus 3 plus 4 and keep going. See, this is the problem with, and up to, well, the next to the last number is n minus 1 and the last number is n. But you see, this is the problem without having some notation is, I've got to do that dot 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 thing, and I have to be comfortable that anybody who looks at this sees the pattern. Okay, but just because I went 1, 2, 3, 4 doesn't mean the next number is 5. Right? I mean, patterns can have all sorts of weird things. I mean, it could be the next number is 6, and then it goes 6, 7, 8, 9, and then skips a number. I mean, that could be the pattern. There's nothing here that truly says it's not. And, that's where, again, this notation is very good because now it makes the pattern very obvious. Okay, so we could do something like that. Now, this is nice. The textbook points out that if this is what you add up, this actually, we have a closed form formula for this. It's n times n plus 1 over 2. And there are a few ways to see that. My favorite way is just to line the numbers up in the two directions. So, here's 1, here's 2, plus 3, plus, and we go down here again to, it's n minus 1, and then plus n. But now, let's add to that n plus n minus 1, plus n minus 2, plus dot dot dot, plus 2 plus 1, and then add it going down, and we see we get an n plus 1 term, but then this next term is also n plus 1, and the next term is n plus 1, and n plus 1, and n plus 1. So you see we have all these terms, but I can tell you exactly how many there are because there are 1, 2, 3, up to n. And so this is equal to n times n plus 1. Well, so that says when I add up this thing twice, so 2 of these, I equals 1 to n, this is what I get. Oh, so it must be that one of those, I equals 1 to n of I, must be half of that, so n times n plus 1 over 2. And they just give you a number of formulas. And then they do point out in their theorem 4.2 that if we have the sum, say I equals 1 to n of c, that is just n times c. Well, why? Because, well, what this says is evaluate the function c, okay, but that function is a constant. So that's evaluate the constant function c at 1 and at 2 and at 3 and so forth, and, you know, all the way up to n. So you see this is my function. So you see my function a sub n is just equal to c. It's a constant. And so we're taking a sub 1 plus a sub 2 plus a sub 3, you know, up to a sub n. But each of those just evaluates to the constant c. So that's c plus c plus c plus c. Well, n times, right? There are n of them. I can tell by these subscripts. And so that's where we're getting that nc. Now, another way to look at this is because it's a sum, right? If I have a common constant in every one of these, the c, right? I can factor out a constant out of a sum. So I could factor that out. If I factor that out, just kind of adding to the string of things that are all equivalent, I could have c times 1 plus 1 plus 1 plus 1 plus 1 n times, and so that adds up to n, and I get n times c. So, you know, this is a nice property of summations, that if I have a sum, I equals 1 to n of a constant times a sub I, well, that is the same thing as c times the sum I equals 1 to n of a sub I. Okay, I can factor a constant out because it is just a sum. All right, well, I think that's enough with this sigma notation, and we'll call that one good.